Welcome to TGLF, where we check out a machine learning paper every month and just talk about it. We're going to share our impressions, go into each other's key points, and talk about what this unlocks for us as ML engineers in the industry as a whole.
Hey, Lucas.
How's it going, TG?
Good. Okay, so how's it going?
It's going pretty well. I got to say, I'm so excited about a Llama 4,
Yeah.
and I really want to get into it. I really want to see what their technical report is. And I also found a paper recently called it is language modeling via diffusion. So it can actually get a couple tokens at a time.
So instead of autoregressive generation, you are generating in parallel?
Yeah,
Okay.
it's not just you can combine autoregression with it, and so it can actually like step out and here's like 10 mask tokens and it'll denoise those and then step out and denoise those. It's super interesting. It's a really cool direction that I want to explore. But
Cool. We can take a look at it in the future session.
yeah,
That
yeah.
sounds interesting.
So for this quantization stuff, I actually did a little bit of vibe coding.
Okay, great.
I let me show you what I did. I got Cursor to make some animations.
Awesome.
Do you see that now?
Yes.
Okay, cool. So I got a couple of different quantization algorithms in here. I was working on the int8, but I couldn't get it done in time. So let me show you what I got, and then if at any point these animations don't agree with your intuition, let's talk about it. Maybe the animation's wrong, maybe I got it wrong.
Okay, let me make sense of what are we looking at. Is it all using this? Is it using same model but different quantization methods? Or
It's just like a
oh, this is the animation.
demo of like as many parameters as I want.
Okay, okay.
So it's
I
not
see.
using actual data. It's not using an actual model.
Okay, okay.
But I'm able to let me just show you the naive quantization.
Can you explain what our X and Y axis are, or what's the range?
Yeah, so up here, like the y-axis is pretty much one parameter per cell.
Okay,
Then
okay,
up here we have like a fine-grained grid, and then down here a more coarse-grained grid. And you see they snap to the middle of the cell. That's them going to the coarse-grained grid. So if I restart, and then you see the trace and what they
uh-huh.
originally were. So this is my understanding of quantization before going into this deep dive. It's just mapping all of the parameters to a more coarse grid. That was kind of my idea initially, but then when
Mm-hmm.
it talked about getting the background for GPTQ, they really
Yeah,
built off of optimal brain quantization.
yeah.
So I tried to animate optimal brain quantization as well. This is just the ordered version, so it's just going from top to bottom, and then I animate a little bit of noise adjusting the rest of the weights, which is what they do when they calculate the Hessian and then recalculate the values of what the other non-quantized weights should be to try to minimize the loss.
Yeah. So between 32-bit and 16-bit, I think that's a good start. But a lot of crazy things happen when you squish that into 8-bit and then 4-bit and then 3 bits, then 2 bits. I think here we are not able to see, much, but we get the general idea where you are moving them to the grid point. But if we were to visualize 16-bit to 8-bit or a 16-bit to 4-bit, then you would see they move a lot.
I'm sure. Let me show you the rest of the algorithms that I visuals for. Maybe we can show this part. So this one is just going to find the one that's closest to the grid point and then quantize that one next. It's the so-called greedy quantization. And this
Okay.
is actually what optimal brain quantization does. And we can, let's see, use this to 128 by. So you can see with each
Yeah.
step, it is actually adjusting the weights quite a bit. And so it would
Yeah.
get snapped to a different grid as compared to if we had just done the naive quantization. But you also begin to see how long this algorithm takes. since it's
Yeah.
doing one parameter at a time.
This is very expensive, right? For some hundreds of billions of parameters, this is going to be expensive.
Yeah.
Yeah.
Yeah. But those insights that they had about how it doesn't really matter what order you do. You don't really need to calculate the greedy, the one
Mm-hmm.
that the parameter that needs to move the least. If you go into batch quantization, this is a lot more similar to what the algorithm looks like. So it's the same number of parameters, but I'm setting the batch size to 16. And you can see it's a
Okay, so you can
huge
do
difference
six.
in speed.
Yep. That's good for GPUs.
Yeah.
So if we are just doing one at a time, I think we're not making good use of the fancy new GPUs. But this one, now you can set a larger batch, then get it done quickly. So the dark blue is where we started. Then you have the purple, and then they settle in the red position.
Yeah. The light blue is where we started, but the dark
Right.
blue is what the parameter value is at that moment. And you
Okay.
see, after we update the batch,
Right.
they adjust the parameters to minimize the
Cool. So now you coded this UI using, sorry,
cursor.
which cursor? Cool. How long did it take for you to get this UI working?
I think like 2 hours, maybe less. It was more just to like, am I right? Am I wrong? I was looking at the paper and then doing this.
Yeah.
I think I spent the last hour trying to get the int8 quantization to work, but it really didn't work. So everything that I showed you, like an hour or less.
If it works, it's in a second. But if it doesn't work, then you're gonna spend a lot of time. Yeah, I
Yeah.
think I have a similar experience with Copilot. It works most of the time, but I had not tried that specific visualization. But for me, Matplotlib, not Escalan, the pandas visualization, they were always, I had to look up the docs to make the UI. It was so time consuming. Now I can just say, Copilot, make this, here is my data frame. Can you visualize it in this way? And it gets it like 99% of the time.
It's great at data frames, and I also
Yeah.
ask it to like explain a piece of code in case it's something
Yeah.
happens. It's good at that stuff, but I would
Yep.
never push that stuff to what I just made to production at all. Never.
All right. So from my end, so my approach to learning quantization, let me see if I can share my screen. So for me, I think the word of quantization is pretty vast at this time. So as you know, very actively worked on, and there are so many methods. Yeah, so we won't be able to get through all of this for sure. It's probably gonna take a whole course to get through all the details. So I thought we can go look into a few of these papers a little bit in depth. So you already talked about, I think, GPTQ.
Yep.
I think the first one is a very interesting one, easy to understand at least. How about we start with int8? I think this is at least Hugging Face used to advertise this very well a year or two ago. So the whole idea is that you have a model and then call .int8 and then your model is quantized. It's how simple it's supposed to work. But for me personally, I think FBGEM is one of the earliest works quantization. So you can see, I think there's a blog post from Facebook from 2018. This was one of the earliest works, 2018, but they reference to a paper that's published in 2017, I believe. So they made this library called FPGEM. Now it's under PyTorch, so very popular library. So we can. The reason I bring this up is the int8 builds upon FPGEM. They say we do this and then we improve FVGEM. So this is a very popular library, and then there are two papers that describes FVGEM. But let's dive into int8 paper and see. So int8 paper, what they do. So the general idea of quantization, right? So you have higher precision weights, something like 32-bit or even 16-bit. Now we are getting down to lower precision. Why we go to lower precision? One, you save less, you need less memory for inference. Two, computation in lower precision is much faster than computation in higher precision. For instance, 64-bit floats or doubles are much expensive than 32-bit, and 32-bit is much expensive than 16-bit, and so on. So this one brought, that's the first part. So higher precision are more expensive than lower precision in terms of pure raw computation. But then data types also matter. So integer arithmetic is much faster than floating point arithmetic. So two things to keep in mind, right? So this one, not only going from 32-bit float operation to 8-bit, it's also 8-bit in integer. So it's a lot faster. So this idea, this thing was actually, I heard about this from FPGen. This is exactly what they were trying to do. So do operations in 8-bit integers. Why integers? Because I think they were targeting for phones. If you want to run some model on a smartphone, 8-bit operations on phone will be faster, consumes less energy. So this paper, I think they talk about quantizing to 8-bit integers. Um, so it's a two-part solution. First, they use vector-wise quantization. The second, I think they have outliers. They build on top of FPGen in, but they improve it with, maybe we're not going to get into all the details, but at high level, so FPGen used to quantize it in certain way. I think they were doing row-wise quantization, if I remember. Maybe that, but this one they say vector-wise quantization. Um, so here is a baseline they compare. So one of the issues they have identified is, as on the x-axis we see number of parameters. Here they are using OPT model, which is the open source GPT equivalent. When you keep increasing the model size, for instance, they start from smallest 125 million and they keep going, increasing the size. At some size, the baseline they have picked, 8-bit baseline, I think they're referring to FPGen, but they're not being very explicit about it. It breaks down. Okay, so here at 6.7 billion, as you see, the accuracy drops. So now they're trying to fix it. That's the setup. So if this FPGen is to work as works for large models, then we have no problem. But here we see we have a problem for large models, which is the case now. Almost everything is huge, massive. That didn't work. So these authors started to fix it. And how did they fix it? The first one, they come up with a so so they have some background information on. So maybe I think this is helpful to understand what FPGen does. This is, I think, Lucas, you already show a nice visualization about how the weights move. Yeah, so here they have, I think, two basic, two in key concept here, amps max quantization. So they go through each vector. This is a, I think, input vector. And they pick the maximum. So they're basically trying to squish weights into this integer range, minus 127 to plus 127 range, and how they're doing it using the max. I think this equation they can see, they're basically scaling it with a scaling term, and that is a function of maximum absolute value. But then they have another method, 0-point quantization. Here the problem is it's not using the full scale of minus 127 to 127. They basically shift. They're using the both min and max to make sure the entire spectrum of this number, the range, is used. So yeah, the improvement, I think this is an interesting section. This is all background, maybe helpful to understand a little bit. But here they say we improve upon one of the most common ways of blocking quantization, which is a row-wise quantization. So this paper they cite is a feature paper. And then they say they're improving it by using vector-wise quantization. That's the first improvement. But that still doesn't solve all the problem they're talking about. Then they, as we saw in this figure, when the model size increases, at some point we see the accuracy of quantized models drop, right? And then they discover this is because there are outlier features. So when we have large models, especially at 6.5 billion or larger, they see there are outlier features.
I think this is an interesting take on this. So, but even though they said they use vector-wise quantization, that's not sufficient. So they're gonna use a fallback mechanism, which is they're gonna identify those outlier features, and then they use 16-bit operations. Here, yeah, I think this is a interesting take. So, you can't, there will always be some outlier features. You can't squish them to this range. Even if you did, there will always be some outlier features that will, because we are dividing by abs values. So they identify those and then they compute in 16-bit operation. That's the essence of this method, right? And so they went into the depth. So I think this is this equation. I think once we understand this, what are they trying to do? Here we see h is our hidden dimension, right? The dimension of our embeddings. Then they divide that into two sets. H belongs to outlier. You see there are 16-bit operations. H does not belong to outlier. You see 8-bit operations. I guess that's the crux of this paper. Simple. The only question now is how do you identify outliers, right? If you have a huge model, then how can you reliably identify outliers?
They must do that with data, and like they have a representative data set, and then they have to just find out which ones give
Yeah,
the high activations.
yeah,
I remember seeing a tweet a couple of years ago about the extremely high activations were often around tokens that seemed to be meaningless to us, like tokens that just have punctuation, that don't really add to the content of the information. Um, often have those outlier activations.
yeah. Um, I think there was another paper. Yeah, some of them you can safely ignore them, right? That's the message. But some we don't know. Some tasks I think you can ignore some of them. For instance, you're producing some creative work. Instead of using a specific word, use another word, and it still makes sense. It's
Mm.
grammatically correct, semantically makes sense. Then you're good. But let's say you are producing a translation and now you are constrained on source, so you have to produce that word. So I think for some tasks, it's safe to ignore the outliers, but some that outliers could make a huge difference.
Yeah,
Especially, yeah, tasks like translation, especially if you don't pick the correct translation of a word, then the meaning can be drastically different. That's the summary I can tell from this. They have some heuristics to select the outliers. So we're discussing exactly along the lines of what you said. You take some sample data set, run through it, figure out where the activations are huge. And they have some heuristics. The magnitude is at least 6, at least 25% of the layers, and affects at least 6% of sequence dimensions. I guess 6% of tokens. That's so. In the previous graph, we saw something crazy happens at 6.7 billion, and then the quality went down. And then this is how they found it. So they looked at the outliers, and they see this is the percentage of layer tokens affected. So I think they saw some emergence of outliers around this size. The solution is just fall back to um, higher precision computation. So in this work, it took maybe this graph may be a bit confusing, but when you look at it closely, my x-axis is reversed. With the model size increasing, you are expecting the perplexity to go lower. So I think it's a bit confusing graph. So on this graph, we see model size increasing. It's the billions of parameters. And here we see perplexity decreasing. Yeah, so that's summary for the first paper.
yeah. Let's get on to the next one.
Yeah. Um, I think the next one is this is probably your favorite, QLoRA.
Yeah, we definitely use QLoRA on a day-to-day basis. It's
Okay.
I mean, it kind of makes sense that to use LoRa to pick up any quality that got lost by just doing a naive quantization. But of course, QLoRA could be combined with GPTQ. So you have a good quantized base model, and then just use LoRa to recover any loss of fidelity that you had.
So for me, this is a natural progression. When I am not using QLoRA in a day-to-day basis, I have played around with this. So maybe I forgot to mention, this is part of this work is the foundation of this library called Bits and Bytes, which is very popular. I'm not sure if the authors have shared it here. So one thing we can observe is you see the first author and second author, and now you see first author and the first author and the last author, first author and the last author, they are same.
Yep.
And then now you see after a few years this paper showed up. Oh no, 1 year, 2022. But now you see something called Bits and Bytes library. And now that even though the link was from our first author's personal GitHub, now it's now part of Bits and Bytes Foundation. I think this library is, as you know, we are not just research scientists, we're also research engineers doing stuff. Sometimes having a good code to work with is very helpful. So there is code for this available in Bits and Bytes library, which we can do pip install and then start using. And this is also very nicely integrated to Hugging Face. This work for me is a progression. When I say progression, the previous work we were looking at 8 bits. Now we are talking about 4 bit. So this is taking it to next step with 4 bit. And here we are talking about, in the previous one we were talking about 8-bit integers. Now we are looking at 4-bit floats. And we can kind of guess why. So there we were talking about inference. We didn't talk about training a model. We already have a model, let's run inference. Inference with 8-bit integers, good to go. Training, we need to be able to backpropagate gradients. You need to have floating point numbers. I'm not sure you can do propagate on integers reliably. So we are now using normal float. So we are looking at 4-bit floating points. And there are many formats for floating points. Have you come across this? There is IEEE standards for 32-bit floats, right? Then there's IEEE standard for 16-bit floats. But then there was a new standard called B float 16. So there are 2 standards to even represent 16-bit numbers. I think FP8, I'm not sure if there is an IEEE standard for FP8, but now we're going to floating point 4. I don't think standards have even established yet. There are so many ways you can represent 4-bit numbers. Then for me, what's interesting is now the authors here have come up with their own 4-bit floating point numbers. That's why I highlighted this saying this is normal float NF4. And they say this is information theoretically optimal for normal distributed weights. That's actually a very clever, I would like to talk more about it later. So they have three takeaways from this. One, they have a new floating point data type, which is 4-bit, and it's they designed this with some goals, which we'll discuss later. Then they have double quantization. The previous LLM.int8, we looked at some scaling terms. They were in a higher precision. So we multiply by some scalars. They were, for instance, you can see, even though we're quantizing to 8-bit here, the scalar is still 16-bit.
Mm-hmm.
So it was not, like when we say int8, it's not entirely 8-bit. Majority of it is 8-bit. Then there are some scalars, some terms that are not 8-bit. So here they are established even those scalar terms. That's the double quantization. Then now we are also talking about training these models. So there is some optimization for training this, time optimization for handling out-of-memory issues. That's the paged optimizer. That's the third contribution. As you mentioned, you already talked about low rank adapter weights. I haven't been playing much with adapter weights, but is there something you'd like to add?
Yeah. So generally, I describe a LoRa adapter as kind of like a rider and its elephant. So the big base model is the elephant, and then the rider, the LoRa on top, is just steering the elephant. And so what you can do is, if you have a very specific task, like extracting information from raw data and then converting it to a JSON so that you can use it in your downstream tasks. You'll find that the APIs are pretty good, but there are still going to be examples where it's not perfect. And so if you have an open source base model, generally that's not going to be as good as the APIs, but if you train the adapter to work on this specific task, the adapters can often be better than what the APIs offer.
Oh, that's interesting.
Yeah. So you kind of have a task-specific driver for this base model. And then if you have two tasks that you want to specialize for, you can actually share the same base model and then just swap out for a new adapter, depending on what you need at that point in time. So
that's actually very cool. So now you can only keep one copy of the base model. But then if you have many subtasks, you can have specialized adapters for each of them, and you can swap in and swap out depending on which task you are using this model on.
Exactly.
And okay, so I don't think I can ever forget rider and elephant analogy now. So we are basically manipulating the rider, and you can switch out rider depending on your task.
Exactly.
Okay. So here the authors are very happy to say they reduced the memory requirement for 65 billion models from 780 GB to less than 48 GB, which is very impressive. And then you can also fine-tune these models on a single GPU. And they talk about like 12 hours on a single consumer GPU. That's very impressive. So until now, I think the previous paper we saw at PGEM was role-wise quantization. Then we saw int8 was vector-wise quantization. And now we are into block-wise k-bit quantization. When we are looking at the matrix multiplication, you're multiplying a row into a vector. The row in the first matrix to a vector in the column vector in the second matrix. Now here they have much more fine. We used to have one scalar for row and one scalar for column, but here if I understand it correctly, you can split that into many blocks. So you can have a hyperparameter p, and then if you have a 512 dimension embedding vector, basically you could now split that 512 dimension into multiple blocks and then quantize them independently. Now they have much more fine-grained control, but that also means now you have, previously for the entire 512 dimension embedding, you had one scalar. Now if you split them into multiple blocks, now you have many scalars.
Yeah,
right?
yeah.
So now you see why they had to go on double quantization, because now we are adding more overhead. They talk about low rank adapters. We already touched that thing, so we can skip. So here, I think there's another interesting point I wanted to point out is it builds on something called quantile quantization, which is also another paper from the same group. They worked on blockwise quantization. So this paper introduced the concept of blockwise quantization. Let's see if I can take you to 15. So yeah, it's 8-bit optimizers via blockwise quantization. So QLoRA builds on top of that. So it's also almost same set of authors. Each quantization bin has the equal number of files. I think the main point here is they use information theory approach to fully utilize all the bins. So one of the problems we have is when we map, in your visualization, if you remember, not all the grids were fully utilized. Some of the grids were all empty. When we map, imagine, I think in your case, you had you almost have a square grid, right? So if you were to see, say, higher precision on one axis and lower precision on the other axis, and when we project higher precision to lower precision, then you see most of them end up in the same region. not even though lower precision, say 4-bit or 8-bit, let's say 8-bit is easy to visualize, 8-bit, we have minus 127 to plus 100. You have 256 bins. Not all bins are utilized. So because the data doesn't come in a uniformly distributed way, right? Most of the data, as you know, normal distribution. So they all center around some data point. So that's the insight they use. They use this information to still spread out to utilize as many bins as possible.
So am I correct in understanding that when they bin these parameters and scale each bin separately, it seems like they are utilizing the coarseness of the grid in
Correct.
a better
Yeah.
way than if they had just
Yeah.
scaled all of
Yes.
them
Yes.
and they all have to.
Because they're not treating input as a single vector. They're treating them as blocks, and now they
Right.
can quantize each block and then assign them to spread them to different bins. It helps. This way, you're not you can distinguish between different data points. They're not overlapped on a same bin. But at the same time, I think the drawback here is it's very expensive. I think that's the point I want to highlight. The process of estimating, the scalars or quantize is very expensive. So you can have a very precise estimation that's very expensive, or you can have some approximations, but they're gonna have outliers. They're gonna have errors because it's approximation. But then what the authors say is, let's take a step back and look at our data. I think this is very deep insight about good research. So they know if you want to precisely compute it, it's expensive. If you try to approximate it, well, it's fast, but you're going to have errors. But what can we do? So we are stuck between these two, right? They say, can we avoid it when the input tensors come from a distribution fixed up to a quantization constant? They look at the data and say, well, the data comes from some fixed distribution. So if you know our distribution, then you don't have to go and estimate every layer, right? So as we know, when we initialize our network, we initialize around 0 with some very small so randomness from 0. So
Right.
because all the models, they're not totally random, because they all have some zero-centered normal distribution. And we also have things like layer norm, etc., to force it into normal distribution. So they say, okay, so since we know this insight about the data, then you can efficiently compute it. I think, if I understand correctly, they're using this to information to efficiently compute the quantiles. So this solved the problem by looking at the data and say, okay, if our data comes from this distribution, that's an additional information. They use that to compute efficiently. Then double quantization. I didn't get into all the details, but double quantization, as we discussed, so they are quantizing the quantization constants for additional memory savings. Because as we saw, they have block-based quantization and they need to double quantize. They take up a lot of space. Now we are talking about 4-bit, and they take up a lot of space and they're quantizing it. I think they're using 8-bit now, even though for 8-bit quantization, the scalars were 16-bit. Now for 4 bits, they're using 8-bit scalars. There are so many evaluation. As you see, I think this paper is 26 pages. This is BF. I consider bfloat 16 as the baseline. You don't even need 32-bit. So if bfloat 16 almost approximate where it's pretty close to the 32-bit calculations. And now, so int8 and even 4-bit, they should have given a model size here that would have helped us. So they're getting the same performance as 8-bit model, even though it is a 4-bit. So they reduce the model size while retaining the same performance. I said that's the main, right? Here are the other floating point formats. If you remember at the beginning, I said, so there are so many floating point formats. So here is the other 2 formats for 4-bit float representation. E2M1 and E2M0, I think. They're talking about how many exponents and how many mantis-bits.
Yep.
You have 4 bits, and how do you split them? I think that's my take on this paper.
The paginated optimizers, maybe I'm wrong. They're super useful if you have shared memory. If your hardware setup has shared memory between the GPU and the CPU. But in my Linux box, I don't have shared memory, so I don't think I am able to use page optimizers.
Oh yeah, so I totally missed this point. It seems to be a new feature from NVIDIA, which I have not come across yet. So I really don't know.
I think it's just the new stuff, but it's basically like your training's not going to run out of memory because it'll offload it to CPU RAM.
Yeah, I think for this work, it's very important because we are forcing a big model into a small GPU, and not just for we're not just running inference on it. We are trying to train. So the chances are the batch consuming a lot of memory, either in the forward step or in the backward step, are high. And then, so it's a very useful feature for fine tuning. So you can tell I haven't been doing QLoRA so in practice yet, so can't comment more. Okay, so the last paper, how are we doing on time?
I think we're doing okay.
Okay, so where do we start? I think you probably have spent more time on this paper. I saw related work, and maybe you would be interested.
Yeah, I mean, on this work, I think I got it with the visualization where they work off of optimal brain quantization, and then that quantizes one parameter at a time while adjusting the non-quantized weights such that they minimize the change that the quantization introduces. And then they go through a model one parameter at a time. And that's super slow. But they noticed that if the order of which parameter that they quantize, that order doesn't really matter too much. And then for the exceptionally large models, they can quantize in batches, which reduces the number of times they need to update the non-quantized parameters. So I can show the visualization again that gets it across. Should we go for it?
Yeah. Should I will stop sharing.
So yeah, over here, again, naive quantization is just snapping to a grid. Greedy quantization is, we're gonna have to speed this up. This is what optimal brain quantization does. It finds the parameter that's closest to the grid point and then quantizes that, but it has to recalculate the value of all of the non-quantized parameters in order to minimize the loss that is introduced, minimize the change that's introduced by the quantized parameters. But as you can see, it's taking super long. So I think the big takeaway that I got from GPTQ is they did this batch quantization where they can the order doesn't really matter, so they do it in batches. And as you can see, that's a huge speed up.
Yeah, if we can batch it then and take advantage of GPUs, then you can do you can quantize large models. Thank you. So from the takeaways from maybe I'll quickly go through a few highlighted portions I had in my paper. In terms of like continuity from our previous work, this one is out of time, I think. So this is around the same time frame as LLM.int8, but before QLoRA. So this work does not reference QLoRA because it wasn't there at the time yet, I believe. So it was uploaded to archive 22. For me, what's the nice takeaway here is, I think you also saw, you can take some data set and then calibrate the model, calibrate the parameters. At least I used it. I tried to do it from the Hugging Face code. So other models, you don't need a huge data set to quantize. So you just need really one shot or one dummy example, you can calibrate it. But here, this GPTQ seem to take, even though they say new one-shot weight quantization, at least in the Hugging Face example, they load a data set to quantize, which was interesting. So let me go back to the Hugging Face overview page. Yep. So when I looked at this chart, I recognize bits and bytes easily. It was maybe I saw it in Twitter or LinkedIn somewhere, and it's also on-the-fly quantization. It means you don't really need a data set. You have a model. You can, even if you pass some dummy text, it works. Then I saw a GPTQ model. It doesn't say on the fly. So my understanding is you actually need a proper data set to calibrate the model.
Yeah.
Okay. But I still like this method because now this bits and bytes stops at 8-bit, it stops at 4-bit. Whereas here you can go down to 3 and 2 bits if you would like. Let's say you're working on really constrained settings. Maybe you just want to test the extreme situation, and you can even quantize to 2 bits. Right? There are only few. Maybe this one's a new addition. Then this is only few that could do this at that time when I looked at it, and that also runs across variety of hardware. Right. So as you see, some of them might run on CPU or might run on GPU, but might not run on Apple. They haven't implemented this, but this looked like, okay, it seems to have most of the greens. So I started looking at this paper. As we saw there, you can not just stop at 4 bits. You can also go down to 2 bits, which is right. You only have 2 bits. You only have 4 states.
I found this really interesting. Ternary quantization levels, that's how, what is it? Bit LLMs? Like LLMs where it's either a -1, a 1, or a 0?
Yeah.
It's ternary, right?
Yeah, I think that's what they're talking about. It's not 1 bit yet. It's not 2 bit. It's somewhere in between. It's not 2 states. It's not 4 states. It's 3 states.
3.
I'm not sure. I actually don't know what's the data type they're using to represent ternary. So you actually need 2 bits, but in hardware, because you can't. There's no 1.5 bit in hardware.
Not yet.
Maybe I don't know how it is done, because my understanding of computer hardware stops right there. Yeah. So this is really interesting. So we know for instance, QLoRA is already doing great at 4 bits, but you can push it. You can go down to 3 bits, and you can go down to 2 bits, or even ternary. My takeaway from this is SC16 is the baseline. So then the 4-bit RTN, I think it is round to nearest. As for this work, RTN, they refer to, for instance, LLM.int8 as RTN. So here they say this is the LLM.int8, I believe. Prior methods only remain this. I believe they said something like round to the nearest. Okay, so they seem to have breakage points at some sizes. They seem to be not very reliable. I guess it's because we saw there are outliers. So here, this one seems to go layer by layer and then quantize each layer. That was my understanding. So layer-wise quantization.
Yeah, it goes layer by layer and then quantizes them in batches. But by doing batches, it reduces the number of times that it needs to compute the Hessian, like the second derivative of the weight matrix.
Yeah.
And they also use a different method to compute the Hessian that's slightly different from what optimal brain quantization does. And that just adds some numerical stability.
Yeah. Okay. So this is I didn't get an intuition for what exactly is happening here. So I didn't spend too much time
from opposite ends.
So yeah, as you see, I didn't spend too much time here. That's all I can say.
I think that's it.
Yeah. I'll stop sharing.
Good stuff, TG. Is there I don't know, after checking out these quantization methods, is there something you want to try out?
Yeah, I think the QLoRA stuff, so considering it's already 4-bit and it seems to be, well, I would try QLoRA. Then GPTQ, I already tried making GPTQ, but it was from the practical point of view, from the coding point of view, I didn't succeed in the simple attempt. But I could get the bits and byte quantization working. That's pretty easy to get started, at least for me, the models I've been playing with. And bits and bytes is also, as you saw, as for Hugging Face. I know in paper, they both seem to take some data set to calibrate or learn the scalars. But in the code point of view, Hugging Face one, we don't need to give a data set. You have a model, it's just on the fly. You don't have to calibrate anything. So it seems easy, and I could just use bits and bytes to start with.
I have used bits and bytes before. I think the reason GPTQ requires a larger data set is because that's how it calculates the difference or the like the loss for how bad this quantization has, how much it brain damaged the model, so to speak.
Okay.
And then to cover for, rogue activations, they need a like a wide variety of inputs. But I haven't done any hands-on work to see exactly what the limits are, or what happens if you only give it one example. Not
Yeah.
quite sure.
And does is the sample important in the sense, let's say, I work in translation. So let's say I have an English-French model. Now I have also English-Spanish model. Do I have to switch my data set depending on what my task is? So if I'm trying to do well on a specific test set, can I overfit to test that test set? Is that a risk? All those questions, there's a lot to figure out.
Yeah, I mean, if you're doing LoRa, then your point is to kind of specialize on a task, and I would say, yeah, use the French data set if you're going to be testing on French. But I think in GPTQ, I would take a little bit of everything that you expect to see, and then that would hopefully allow you to just see a wide variety of everything. But I was really interested to see that you can get it down to ternary. So I'm wondering, Meta just released Llama 4, and there's that 2 trillion parameter model coming out.
Oh
So
yeah, I don't think
what?
we can run it.
I know I can't run it, but if we took the 2 trillion parameter model and then reduced that to ternary, then it's a
Yeah,
bitwise LLM. So
yeah.
is that like a shortcut to go from we'll let Zuckerberg train it, and then we have this essentially bit LLM? I don't.
Right. Even if it's 2 trillion parameter, even if we are getting the weights in 16 bits, which is SBF 16 is what most people distribute, you still need 4 terabytes space to put that on a disk. Now, yeah, I don't think there is even a hope to, okay, download 4 terabytes, put it on a disk, load it, run inference. I don't think that's happening. So we have to get to, even if we go to 8 bit, you still need 2 terabytes. We are still talking in terabytes, right? Even if you go to 4-bit, you're still talking about 1 terabyte. So you have to go to 2 bits or maybe ternary. Then you are in the size of 500, half a
100-ish?
terabyte.
Yeah.
Yeah, yeah.
Yeah, I don't have GPUs that can run that thing yet. But, one can dream. One can dream.
Yep. But the other models they have released, 17 billion active parameters. I think that's
Yeah.
we can first try on that. Yeah. So my updated take on this is I would really like to get the GPTQ working. Once I have the practical side of it, okay, I have my own custom model. I want to run that. And then once it works, then I am all up for take it down to, okay, 4-bit, 3-bit, 2 bits, maybe ternary, and then see how the performance degrade. I don't think we looked into the results. What happened? How much is the loss when you go from 4-bit to 3-bit to 2-bit to ternary?
Yeah, they didn't show.
Yeah, and I don't know even if that those results are generalizable to our task. So we still have to evaluate it ourselves.
Yeah, I think from a business standpoint, Aura is the move that I would go towards. Particularly, I don't even know exactly if I would quantize the base model. I would just quantize it or prune it just to the point where it'll fit on the GPU, and
Yeah.
then have like a farm of LoRa's, each for the specific tasks that I care about.
All right, Lucas.
Good stuff, TG.
Likewise. Okay, disclaimer, this is all our personal opinion, doesn't represent our employer, just two people hanging out and chatting.
Yep, just personal opinion. Yeah.